Okay, Bismillahirrahmanirrahim. Electronic circuit design. It's a new course that has been launched by the Board of Studies for the communication students. So let's start with the first chapter. So briefly, we will explain the very basics of the electronics, and the electronics starts from the semiconductor theory. So it's our first topic. So the atom consists of a nucleus, as you all know. Electrons in several orbits move around the nucleus. It contains three basic particles: protons, which are the positively charged particles, the neutron, which are the neutrals, and the electrons. So the charge on proton and the electron is same, that is 1.62 into 10 raised to the minus 9 coulombs, but they are oppositively charged bodies. Okay, so the protons are inside the nucleus while the electrons are rotating outside in the shell. So here is a structure of the atom. Okay, so there is a hole and electron concept in semiconductors. For example, this is the silicon atom and this is the germanium atom. So as you know that both of these are belong to fourth group. So that is why there are four electrons in the outer shell. Okay. So usually the protons and electrons will be equal in number. Therefore, atoms are normally neutral electrically. If an atom loses an electron, it means it has lost some negative charge and hence has a net positive charge and vice versa. So, having a look on these two atoms, this is the silicon atom and this is the germanium atom. So, electrons can occupy only some fixed orbits. These are called the shells. Each shell can be occupied some by only some specific number of electrons. The outermost shell, called the valence shell, may be only partially filled by electrons. So the figure shows a 2D simplified orbit arrangement of silicon and germanium atom. Absence of an electron in a shell is defined as a hole. Okay, so the deficiency of the electron is actually the holes. So the silicon and germanium atoms are electrically neutral. Outer shell has four holes and four electrons each. So either they have to lose these four electrons or to gain four more electrons to complete its outermost shell. Okay, so here is a figure 1.3. So these are the atoms, okay, and the arrow shows the free electrons. So the electrons are negatively charged particles and these electrons are repelled by the negative voltage, therefore they will move towards a terminal where positive voltage is applied. Holes are, on the other hand, holes are the positively charged particles. So the holes are repelled by the positive voltage and they will move towards a terminal where the negative voltage is applied. Okay, so please note the direction of the current flows is always opposite to the direction of the flow of current. So now N type and P type, you may be familiar with these two type of semiconductors, and these two are introduced after the doping effect, and the doping is done in order to start some motion of electrons or holes, and the way of for the conduction is provided. Okay, so the intrinsic electrons are those which are the pure and no doping is involved. So because of no doping, uh, their conductivity is very poor and very rare. So in order to improve its conductivity, we have to make it extrinsic. So extrinsic semiconductors are those semiconductors uh, 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 by which in which small amount of the impurity is added with this pure semiconductor. The conductivity of the semiconductor is increased by this way. Such material are known as extrinsic semiconductors. The deliberate addition of a desirable impurity is called doping. Doping yields two types of the semiconductors, that is the p-type and n-type. The impurity atoms are called dopant. Such a material is also called doped semiconductor. Okay, so silicon and germanium are the standard semiconductor atoms used by the industry. Some of the popular dopants used in doping are the trivalent, uh, that is the boron, aluminum, etc. Means the third group elements are the trivalent and okay, and by introducing these atom, we can get the P type extrinsic semiconductor material. On the other hand, pentavalent can also be used. Pentavalents are belongs to fifth group. These are the arsenic and phosphorus. Okay, and by introducing these pentavalent atom with the pure semiconductor, we will get N type of the material. So it means uh, in P type, the holes are the majority carriers, while in N type, the electrons are the majority carrier, because by introducing the n type we will have one extra electron, because in pentavalent we have the five electrons in their outermost shell, while the silicon and germanium have the four electrons, so 4 plus 5, that will be 9. It means one is extra. So it means this extra electron for each atom will act as uh, the conduction particle. Okay, so it means in n type the electrons are a majority carrier, and p type, in p type the holes are in majority carriers. Okay, so here is a demonstration of n type. Okay, so this is the one extra uh, electron I was talking about, and this is the p type. The boron third group element is added, so it's a trivalent. So you can see there is a deficiency of one electron, because now we have 7 electrons in the outermost shell by sharing the trivalent with the semiconductor uh, element. Okay, so it means we have the holes in a majority. Now we have to merge these two. By combining these two we will get p-n junction. Okay, so this is actually the basic element for any electronics circuit, means the diode. Okay, so there will be a diffusion when these two will be touched. There will be a diffusion. Okay, so there will be motion of electrons and the holes. So few electrons close to the junction start crossing the junction to reach p side, while few holes close to the junction start crossing the junction to reach the n side. These electrons combine with some holes in the p side to create some negative ions, while the holes with the electrons in the n side to create some positive ions. Due to these ions, a negative voltage built up. So this is called a barrier voltage. Okay, and similarly on the ends and the p side, we will also have a barrier voltage. Okay, so this is a barrier. Okay, because electrons have uh, crossed this junction and moved towards the p side, while the holes crosses this junction and move towards the n side. Okay, so this is a depletion region. So in order to start the conduction, first the electrons and the holes have to cross this barrier, and for this purpose a barrier voltage is, at least a barrier voltage is required. So for the barrier voltage for the silicon is zero point 0.7 volt, and that for the germanium is zero point 0.3 volt. Okay. At around the barrier voltage, electrons from the n side are repelled by the negative barrier voltage in the p side, and similarly the holes from the p side are repelled by the positive barrier voltage in the n side. Therefore further diffusion stops. Okay, so what is the depletion region? In the diffusion process, as mentioned above, when the voltage barrier potential is reached, further diffusion stops. So no charge carrier, both of electrons and holes, will be present close to the junction. Only ionized atoms, that is positive and negative, will be present on either side of the junction. This region is known as the depletion region. It can be shown in this figure 1.7. Okay, this is the depletion region. Okay, so now we have to bias this p-n junction. So there are two type of biasing. One is the forward biasing and one is the reverse biasing. So let's start with the reverse biasing. And next, when an external voltage is applied, that is DC, to a diode, that is a p-n junction. So the p side is connected to the negative terminal and n side is connected to the positive terminal, and this type of biasing is called what? The reverse biasing. So by the reverse biasing, the depletion region will be wider and wider. So it will cause to increase the barrier more and more. So conversely, we can say that the conduction, there will be a wider barrier for the conduction of the electrons and holes. So there will be no conduction at all because the barrier is increasing. So in order to cause a smooth conduction, the barrier must be reduced. It means the depletion region must be diminished. Okay, so by reverse biasing, uh, the increase of the barrier voltage causes the barrier voltage and n type becomes more positive, and the barrier voltage at the p side become more negative. So electron from the majority carriers in the n type are repelled away from the junction and are attracted towards the positive terminal. The holes, these are that are the majority carriers in the p type, are repelled away from the junction and are attracted towards the negative terminal. So consequently, depletion region further widens and the barrier voltage increases as shown. So at a result, majority carriers cannot flow across the junction, and therefore under reverse bias condition, no current flow is possible. In other words, forward current does not flow. So now what we have to do? We have to do the forward biasing in order to diminish or collapse this depletion region and start the smooth flow of the majority carriers on either side. Okay, so what is the forward biasing? When an external DC voltage is applied to the PN junction such that N side is connected to the negative terminal and P side is connected to the positive terminal. So this type of biasing is called forward biasing, and it will cause the reduction of the depletion region. Okay, this biasing arrangement decreases the barrier voltage as shown in this figure 1.10. As you can see that the depletion region is decreases. So the barrier voltage at N becomes less positive and the barrier voltage at the P become less negative. The electrons in the N side are attracted across the junction towards the P type and are attracted towards the positive terminal. Holes, which are the majority carriers on the p side, are attracted across the junction towards the n side and are attracted towards the negative terminal. So consequently, the depletion region decreases and the barrier voltage also reduces as shown in figure 1.10. Okay, so as you can see, P is connected to the positive terminal of the battery and N type is connected to the negative terminal of the battery. So this type of biasing is called forward biasing. And in this figure, you can see that the p type is connected to the negative terminal of the battery, and n type is connected to the positive terminal of the battery. That is why it is called reverse biasing. So, what is the result of doing the forward biasing? We will The majority carriers will flow across the junction, and therefore, under positive bias condition, current flow is possible. In other words, forward current flows. So, now, as I've already told you, that a minimum voltage must be applied so that this barrier is crossed. So for the silicon, it is zero point 0.7 volt, and for the germanium, it is zero point 0.3 volt. Okay, so that was all about the basics. So then we will move forward towards the uh, chapter 2, that is the semiconductor diode and its application. Okay, so that was a quick uh, intro of the basics of the semiconductor. Okay, so thank you for the moment.